So the first question is going to be an electrochemical cell is constructed using the two-half cell. Okay, so you can see from this question here, they mentioned that okay, this one is going to be Br2 and Br minus. So it's a gas and ion. Okay, gas and ion. So if you have gas and ion, okay, the electrode that we use is always platinum. Okay, and then you have aqueous and aqueous. Okay, or ion and ion. So the electrode that you must use is going to be platinum. So state the material used. Okay, just state. So platinum. Okay, and then platinum. Okay, be very careful. Unless we are talking about metal and metal ion, then you use that same metal. Okay, so this one is going to be important. Now the cell is operated at 298, and they are asking, they are telling the Br2 and Br minus half cell has standard condition. So standard condition is 1 mole per dm cube. So no issue with that. Okay, but the problem is going to be the Mn3 plus and Mn2 plus. Okay, it's going to be a different concentration. They are non-standard condition. Okay, so what we need to do is, okay, we need to use the Nernst equation, okay, to calculate the E. So this is going to be non-standard condition. So whenever you have non-standard condition, the formula is going to be E. Okay, hold on, yeah. Okay, the formula. Okay. Okay, let me open it again. Okay, the formula of Nernst equation is going to be the E. Okay, E is going to be E standard. Okay, E standard plus 0.059. You please remember this. Okay, 0.059 divided by Z over there. This is Z is going to be the charge or the number of moles of electrons that you use. Okay, and then you times with. Okay, normally they put in your book and in my I think in my PowerPoint slide also, I put log oxidized form. Okay, log oxidized form. But please remember, okay, we didn't put the reduced form, okay, because the oxidized form and reduced form, because in that example in the textbook, okay, they put it as a metal. Okay, so do remember, if you're talking about metal, okay, copper 2 plus 2 electron to give you copper, for example. Okay, so if I put the here follow the oil rig, okay, oxidation is loss of electron, reduction is gain of electron. So you see this one, Cu2 plus is being reduced. Okay, it's been reduced. So this Cu is the reduced form. Okay, reduced form. Now, reduced form, when your reduced form is going to be in form of metal, you don't calculate the concentration of metal. Okay, that's why the reduced form is constant. Okay, that's why in your textbook they say log oxidized form only. Okay, but you must remember the actual formula is not that. The actual formula is oxidized form divided by reduced form. Okay, so here is very important because there's oxidized form and reduced form. Okay, so here when you look over here, when I put the Mn3 plus, okay, when they add electron to give you Mn2 plus, I need to identify which one is reduced form, which one is going to be oxidized form. So when I see it here, I know something is gaining electron. So this is being reduced. Okay, Mn3 plus is being reduced. So Mn2 plus is going to be the reduced form. Okay, so Mn2 plus is a reduced form. So this is reduced form. So that's the first thing that you need to find out, yeah, which one is the reduced form. So when I use the formula, okay, 1.49, I get it from your data booklet under the standard condition, okay, 1.49 plus 0.059 divided by what, okay? So here, okay, the Z is going to be 1, okay, but if you have copper, the Z will become 2, okay? Please be very careful on this. Okay, so it's supposed to be 0.059 divided by Z. Okay, so that's the formula. Okay, but in this case, divide by 1. So log what? Okay, log oxidized divided by reduced. Okay, I do not know how you're going to remember. Maybe you remember by OR. I don't know. Okay, please remember this. Okay, so oxidized divided by reduced form. The reduced form, okay, I know that it's going to be 0.1. So 0.1 is the reduced form. This is oxidized form 0.5. Then I use the formula and I calculate, I will get 1.53. Okay, so when you give your answer, please include plus. Okay, plus 1.53. Okay, now we want to calculate the E cell under these conditions now. Now, we will not use 1.49 anymore, okay, because this is a non-standard condition. So we will use whatever that we calculated over here, 1.53. So I put, okay, the equation 1.53 over here, okay. Once I have that, okay, I will look at the periodic, my data booklet, what is going to be the E value for BR2, okay. So BR2 to become BR minus. So when I compare, okay, I want to compare, I need to find out which one is more positive. Okay, then I put them to the right. It's moving to the right or something like that. So here I can see that 1.53 is going to be more positive than 1.07. So this will be moving to the right. Okay, so if this is moving to the right, yeah, maintain 1.53 is positive. But I know this one will move to the left. If it is moving to the left, then it's supposed to be negative 1.07. Okay, so when I add this, okay, what I'm going to get, I am going to get positive 0.46. Okay, and this is going to be the extension to that. Okay, what actually happens, this is going to move to the right. Okay, move to the right, and this one moving to the left. So BR minus to become BR2, BR minus to become BR2. Okay, but you need to balance the electron, because the 2 electron here, you need to times by 2. Okay, do not ever times 2 over here for EM. Okay, please remember that. Okay, so you times 2 because you want to eliminate the electron and electron will cancel. Okay, here you are going to get this equation. Now, please be careful. You can double check the marking key. Okay, your marking key is not always correct, right? Even though it's coming from CIE. Okay, your marking key has error. Please check. Okay, in your marking key, they ignore the 2. They put 1. Okay, that is wrong. Okay, you must have 2 there. Okay, so please double check. Okay, double check. Don't follow blindly. Okay, what the marking key has written. Okay, double check. If you're not sure, okay, just ask me. Yeah, I will try to help you out. Okay, but okay, I have written over here. You know the aqueous condition, aqueous, and then this is gas. So I write down. Okay, now, okay, please check. Marking key has error. Next, okay, this one. The other day, Jody has asked me also. Okay, it's good. He asked me also, so it's okay. I'll show you again. An aqueous solution of copper 2 sulfate is electrolyzed, okay, using copper electrodes. A current, okay, is passed for 3 hours, and then you are going to have certain mass deposited at on the cathode. Okay, the charge is given. Okay, the relative atomic mass is given. So we want to find the Avogadro constant. Now, you cannot use the normal way, okay, of us calculating, okay, like copper 2 plus 2 electron to give me copper. I cannot use the normal way for this, like saying that, oh, 2 Faraday is going to give you 1 mole. Okay, I do this calculation, then I try. Then how are you going to calculate the Avogadro constant? Okay, so you cannot use the you should not even use the Faraday. You should not even use 96500 column over here. Shouldn't. Okay, you shouldn't. Okay, so this is going to be, we are going to use like I think we did an activity about investigating Avogadro constant. Okay, so that investigation when I did, okay, was done, okay, even before this question actually came out in this paper. Okay, so I was using it in 2018. Okay, so you see a 5 marks question came, okay, based on the worksheet that I've created before that. Okay, so it means it's possible that they try to ask every single type of question, investigating and so on. They don't like to ask the same thing over and over again. So this is a very interesting question. So how do we do that? Okay, Q equals to IT. Okay, so you just put the I is 1.5. Okay, 3 hours, you change it into per seconds. Okay, times 60 and 60. So you have this. So what do we have over here is I know, okay, when you have in this, okay, equation, if you have, okay, 2 moles of electron, okay, 2 moles of electron, and you see 2 moles of electron, and this it depends on the Avogadro constant, because we know every one Avogadro constant is going to represent for 1 mole. Okay, so I'm just going to use the L as my Avogadro constant. It means that 2 times Avogadro constant, okay, and you times with the charge, okay, of 1 electron. Okay, when you have that overall charge, 1 electron, they have 1.6 times 10 negative 19 charge. Now I have 2 moles times 2, and it's not only 1 electron. Okay, it's going to be for 1 mole of electron, and we need to know 1 mole got how many electrons. So they represent using L, which is your Avogadro constant, and that will result in formation of 63.5 gram of copper, which is 1 mole of copper. Okay, so that's your equation number 1. Your equation number 2 is resultant to what you have. Okay, 16200. Okay, 16200. It's going to deposit 5.09 gram. I just put 5.09 gram. Okay, so you have equation 2. Okay, what is the relationship? This and this, they follow the same relationship. So if you want to find, okay, the relationship between them, okay, it's the same. 1 divided by 2. Okay, it means that this equation, if you divide them with each other, okay, you are going to get equal. Okay, so it means that with when I put this, okay, when this one divided by this, 63.5 divided by this, okay, I can find out, okay, the relationship is going to be the same. I can find out what is going to be the L. Okay, so I just calculate what is the L. Okay, just calculate L, and you get this. Okay, I supposed to get 6.02 times 10 to the power of 23. Okay, but I'm not getting that. Okay, to explain why, I think because of the experimental error and the conditions and so on. Okay, but you are getting something closer to Avogadro constant. This is what we want. Okay, 6.32 times 10 to the power of 23. If you are not sure, okay, just WhatsApp me. I can pass you the investigation that I've done previously with you. Okay, the worksheet, I'm still keeping it. Okay, so you can also go through that. Okay, because it's the same. Okay, how do we predict Avogadro constant? Okay, using experimental data. Okay, this is the way. Yeah. Now, next question. Explain why magnesium metal cannot be obtained by electrolysis, okay, of dilute aqueous magnesium sulfate. We have done this similar question before. Okay, same. Okay, you have MgSO4. Okay, MgSO4, you have Mg2 plus and SO4 2 minus, and it's in aqueous, so you have H plus and OH minus. Okay, now we are talking about cathode. So there are 2 types of ions will go to cathode, Mg2 plus and H plus. Here at the anode, you know basically which one will be discharged. Okay, the OH will be discharged. Why? SO4 2 minus is a very big very big ion, so they don't get discharged easily. So OH minus will be discharged. But that is not the question over here. They are asking, okay, why you don't get magnesium. So it means you have these 2 equations. Okay, the Mg2 plus will go there, and also H plus will go there. So I write down the equation. Okay, if let's say they got discharged, what is going to be the E value? Okay, the E value from the data booklet, negative 2.38, and the E value, this one is 0. Everyone should know about this. Okay, so when you compare them, okay, you will see that which one is more positive. You can see that this one, the H plus, is more positive. So therefore, okay, the H plus will receive electron to form hydrogen. Okay, in comparison to magnesium. So that is the one that is going to happen. Okay, this is what we call the H plus will be selected and will be it will be selected, and it will be when last time when you learn about electrolysis, okay, when you learn about cell electrolytic cell, why H plus is selected. Last time you learned according to reactivity series, Yeah, the H plus is lower. I'm selecting H plus, but this is the actual reason. Okay, this is the actual reason why H plus will be selected, because it's easier. Okay, it's easier to add electron. What is adding electron? So it's going to be reduction. Okay, reduction is gain of electron. Okay, so it means it's easier to reduce H plus compared to reducing Mg2 plus. Okay, that's the reason. Okay, that's the reason. So here, when you write down, you can write down hydrogen is produced instead. Okay, and you can also include, okay, the reduction of H plus is more easier, okay, than the reduction in Mg2 plus. So that is going to be what we are going to explain over there. Okay, so it's going to be more easier than you are trying to reduce the Mg2 plus. Okay, any question up to here? I will still record. Okay, you see here, I'm not going to write now. Okay, so you see here, explain what is meant by the following terms. Okay, what is going to be half-life of a reaction? Okay, what is half-life? Okay, half-life is the time taken, okay, for an amount or the concentration of the reactant to become half of its original value. Okay, so this one is taken directly from the marking key, but if you want to answer, I will just suggest you to answer it this way. Time taken for the amount or the concentration of the reactant to become half of its original value. Okay, to become half of its original value. Now, rate determining step. Okay, rate determining step is the slowest step in the reaction. Don't write slow step. Okay, I've seen some students write slow step. No, there are many slow steps. Okay, so you need to tell which one. Okay, so the slowest step. Okay, that will be the one that will be the rate determining step. Now, the reaction between hydroxide ion and bromomethane is first order. Okay, with respect to OH minus, and first order with respect to this. Okay, so now we are going to ask you to suggest a practical method that will confirm the reaction is first order. Now, this is very, very important. Okay, because when we learned about how do you do the practical method, okay, what are the practical method that we can use? Okay, remember about quenching and so on. Okay, so the one that we learned. Okay, is it continuous? Okay, is it going to be sampling method? Okay, you do not need to focus on the term. Okay, but they are asking you, okay, how you're going to do this. So here, the one that I can think of, okay, is it going to be continuous or sampling? I think I'm going to use the approach of sampling. Okay, I'm going to use the approach of sampling. But here, how do you confirm? Is going to be first order with respect of OH minus. Do take note, okay, CH3Br is also first order. Now, if you want to only focus on one, okay, you must make sure you use the excess CH3Br. Okay, if you use excess CH3Br, this will make sure that whatever results that you are going to get is only responding to OH minus. Okay, so that is going to be the first thing you need to take note. I am going to use several experiments with different concentration of OH minus. Okay, I'm not going to do continuous method. I am going to control the temperature, okay, so that everything is going to be the same temperature. And I'm going to measure the time. Okay, the time for what? Okay, the time that I'm going to get the concentration. Okay, to become, it means what is the time taken, okay, for the reaction to happen or to finish. Yeah, so here I'm going to find, okay, the concentration of the OH minus in sample. Okay, I'm going to find the concentration of OH minus in sample. And how do I find that? Okay, I'm going to titrate, okay, using something, okay, that can make me find out the OH minus. So maybe I titrate with acid. Okay, or you can use a pH probe. Okay, you can use a pH probe, or okay, you can also find out the concentration of Br minus. How? You can find out by using silver ions. Okay, you can find out the moment the precipitate of AgBr form. Okay, that's going to be the concentration of Br. You can find out all that. whatever things that you have done over here, okay, we can process the results, okay, by plotting the graph of concentration, okay, against rate. Okay, we can plot the concentration against rate, and we try to, or you can try to evaluate the rate, okay, by using the table. If you can say that, okay, when you increase the concentration of OH minus double, if you can find out the rate become double, then you can say that this is going to be a first order. Okay, that is what they say, evaluate the rate is proportional to OH minus numerically. Or you can plot the result. If you plot the result, okay, you see when I plot the result, I even draw the graph here. I sketch the graph here. When you plot the result, okay, you are plotting against either concentration against time or concentration against rate. Okay, so if you plot against concentration against time, okay, we are talking about first order. Okay, first order, then you're supposed to have a curve. Okay, but the curve is going to be, there are two types of curve. Okay, one belongs to first order, second belongs to second order. That one you have to follow the half-life. Okay, if you can find out the half-life is constant, then it's going to be first order. Okay, if the half-life is going to be different, then it's going to be second order. Okay, or the best way is to draw the concentration against rate. Okay, the concentration against rate, the zero order is going to be the constant. Okay, the straight line, and then first order is going to be the straight line, the one that is starting from the origin. Okay, so that is going to be the first order, and then second order is a curve. So since we know it's going to be a first order reaction, we are expecting to get the straight line passing the origin. Okay, so that is what we are going to look for. So if you can explain all this, okay, and if you match 4 of these criteria that they are asking over here, then you will get the 4 marks. Okay, so please explain. But for me, if you ask me what is the most important points, this one, okay, very important. You are going to measure the time, yes, okay, you are going to measure the OH, and we are going to plot the graph, okay, and explain a little bit about the graph. You see, not so much, okay, but I think you need to make sure that you mention that you are using excess CH3Br, or sometimes the question will ask why you need to use excess CH3Br, okay, when you are doing this analysis, to make sure, okay, that the rate is only responding to concentration, change of concentration in OH minus only. Okay, that's going to be the answer. Okay, so you are going to actually eliminate, okay, you are going to eliminate the changes involving CH3Br. Okay, so that's going to be the practical methods. Okay, so now I will start writing. So here you see they say the hydrolysis, okay, of methyl ethanoate, okay, with hydroxide ion is the first order. Okay, and then first order to with respect to OH minus also. So they are asking, okay, they are asking that the rate of reaction is given, so we just put in, okay, the rate equation. So K CH3 CO2 CH3 and everything, you just put it over there, and then you the question is you need to calculate the value of K. Okay, so you can see my calculation over there. Okay, you can have a look. Okay, but anyway, I will see the chat. Okay, Justin has a question. Okay, sir, I got a similar question. Okay, and the answer was does not change or change slightly. Justin, can you explain more? Justin? Oh, for why it is going to be excess. Okay, so this one, okay, when you put something in excess, okay, the when you put let's say for example, okay, if I know X and Y, okay, when I put in this reaction, okay, and then you are going to, we know that, okay, x plus y plus z to give you something. And I know that x and y, okay, both of them, they are going to be involved in the rate equation, for example. Both of them are involved in the slow step, for example. So when I have that, okay, both of them, they are going to change accordingly. Okay, so how do I just focus on identifying the changes involving x only? Okay, so what we can do is, okay, we can increase the concentration that y. Okay, you try to increase the concentration of y, and we can try to when you do that, you are eliminating, okay, you are eliminating the influence, okay, the influence of y when it comes to the rate of reaction. Okay, so it means that we are just focusing, or just, I think the chances of the x changing and affecting the rate is going to be just depending on the x alone, and it's not depending on y because it's in excess. So it means we know there's a lot. Okay, so we eliminate, okay, the y. So if you are going to test only for y, then what you need to do, you need to make this into excess. Okay, so it means what the reason is why we don't want to have any changes related to the y. It means we are trying to eliminate the effect of that one reactant towards the rate of reaction. Okay, but you can read more about this, Justin. Okay, read more about this. But this one is one of the in the practical, we always put excess. Okay, and when you put excess, the concentration and then the relationship to the rate is going to become constant. Okay, it's going to be constant. Yeah. So basically, to make the concentration constant, so it doesn't affect the rate. Yes, correct. Okay, that's the answer. So we want to make the concentration constant. Okay, so the rate will be constant also for that. Okay, so that's the explanation. Okay, that's the explanation. Okay, next. Okay, if we move on. Okay, number 3. Okay, ammonium chloride. Okay, dissolve in water to make an acidic solution. Okay, so calculate the H plus. So they already gave you 4.89. pH is 4.89. Okay, use the formula. Okay, 10 to the power of negative 4.89. Yeah, not 10 to the power of 4.89. Okay, please use that. 3 significant figures. Okay, you have H plus. Calculate the pKa value of ammonium ion. Okay, so ammonium ion, okay, Ka equals to concentration of ammonia, concentration of H plus divided by concentration of ammonium. Okay, but take note, these two concentrations are the same. Okay, so we are taking it as H plus to the power of 2. Why? Because ammonia, okay, ammonia concentration is the same as concentration of H plus. Okay, so you have this formula. And this formula also, there are assumptions. Okay, what are the assumptions? The dissociation of ammonium ion, okay, is too little. Okay, it's too little until we only use the initial concentration. Okay, so we use that formula for pKa. So H plus we have calculated, just put the H plus over there. And then ammonium ion, okay, they already give you 0.3, just put 0.3. Okay, and then you get the answer for Ka. Once you have the Ka, pKa is negative log Ka, you get 9.26. Now, I want you to focus on the assumptions. Please remember this, okay? They normally don't ask, okay, but there are high possibilities where they will ask about this. Okay, what are the assumptions? Okay, the assumption is, okay, we are going to assume that this is going to be the same, okay, and then we are going to also assume, okay, the dissociation is too little until we use the initial concentration of ammonium ion. Okay, so that will be the assumptions. Okay, now, so you calculate, you get 9.26. Now, a buffer solution can be formed, okay, by mixing ammonium chloride and ammonia solution. Explain with the aid of equation how this one can behave as a buffer. So I write down the equation also. Then you, how to explain, you please explain yourself. Yeah. So H plus, okay, when you add H plus, it will react with the base. The base is going to be ammonia, and then you are going to get ammonium ion. Okay. Now, if you have OH minus, okay, if you have OH minus, it will react with the acid. Okay, the acid is going to be the NH4 plus, and then you are going to get ammonia and this. Okay, it's still okay if you write OH minus plus H plus to give you water. Okay, but I will suggest you to use this equation instead. Okay, because it will show us that there is a buffer. Okay, so please take note of that. Okay, and then explain. Okay, so when OH is removed, okay, there is no change in pH. When H plus is removed in that way, there is no pH. And then because there's ammonium ion, there's so many ammonium ions. So the changes that happen over there, okay, will not be because it's too much, in excess. So we are not going to change much. Okay, something like that. Okay, the same thing, whatever ammonium ion that is being used, when they decrease, it's not going to affect the overall concentration. Okay. Now, use the value of Kw. Okay, Kw, okay, you should know Kw is H plus and then OH minus. Okay, and then this one is the same. So we always use this formula for Kw. And this value you need to memorize here. Okay, 1 times 10 negative 14. Okay, pure water. So when you have this, okay, H plus is 1 times 10 negative 7. Okay, this is going to be the answer. Now the pH of pure water is going to be, you see, different temperature. Okay, you are going to have different pH. Okay, so we need to calculate the Kw at 50 degrees Celsius. Okay, so how to do that? Okay, so they have given you the pH. Okay, just use the concentration. Just use the calculate what is going to be the concentration of H plus by using the formula. Okay, just use 10 to the power of negative 6.64. You will get the concentration of H plus. Then we use the formula. Okay, use the formula, and then you will get the Kw. The new Kw is going to be this one. Now, do remember Kw. Okay, at normal condition, the standard condition. Okay, it's going to be always 1 times 10 negative 14. Okay, but when you increase the temperature, okay, to 50, you can see the Kw now is going to be more, okay, than what you have at the standard condition. Okay, this is why, okay, because, okay, if you follow H2O, okay, to become H plus and OH minus, there will be delta H. Okay, so I want to ask you now, okay, that delta H, okay, based on the information that you have now, okay, 1 times 10 negative 14 and 5.25 times 10 negative 14. I want to know, okay, whether your enthalpy change over here, is it positive or negative? Victoria? How to predict the enthalpy change for this reaction? Is it positive or negative? Using the information of the Kw. Your Kw is increasing. Okay, it means it's moving forward. Okay, when it moves forward, this is going to use the LCP principle. Okay, the temperature earlier 25 degrees Celsius. When you increase temperature increase, suddenly it's moving forward. So how to identify? Just see, when this is positive, this is going to be cold, this is going to be hot. So when I increase the temperature, okay, I need to decrease the temperature. How do I decrease the temperature? By favoring towards cold. Okay, so you can see here, okay, it's favoring to the right. So here we say the temperature, higher temperature, okay, favors endothermic reaction. I hope you still remember this. Okay, temperature increase, it favors endothermic reaction. So the position of the equilibrium moves to the right. That's why the Kw increases. So if I ask you to predict, this is going to be positive. Okay, this is positive. So this is by using this information that you have. So it means that on top of this 1 mark and 2 marks, okay, I can give you another 2 marks. Okay, if I design a question, okay, predict okay, the predict what is going to be the enthalpy change, okay, for ionization of for this. Okay, so the equation, okay, predict then and then give reason. Okay, give reason. So I can say based on what I said just now, okay, you just tell, okay, it's going to be endothermic, okay, and then why, okay, temperature increase, it favors endothermic, your kW increasing. Okay, so once you relate that, I think even 3 marks it can still go. Okay, and it's still it's a level 3 question. Okay, so you can also refer to that. Okay, but anyway, let's move forward, move on. Okay, number 4, okay, the table shows some standard entropy data, and then I need to calculate the entropy change for this reaction. So this one quite simple. Okay, this is going to be entropy of product minus the entropy of the reactant. Okay, so please remember the 2. So you need to times 2 times 69. Okay, then oxygen, okay, 205 minus the reactant. So make sure you times by 2 also. You will get positive 189. Okay, positive 189. But be very careful, it's joule. Okay, now use the value, okay, to calculate the temperature at which this temperature, this reaction will become feasible. Now, this reaction will become feasible normally when your Gibbs free energy become negative. Okay, but if you want to use this formula, then you need to use the Gibbs free energy equals to 0. Then only we can find out what is the temperature. Okay, so the temperature when it becomes feasible, okay, or the temperature when it becomes 0, okay, is going to be at this temperature. And how do I use that? Then you need to use this formula, Gibbs free energies formula. Okay, if you remember how I asked you to remember, okay, or you have your own way to remember, please remember that. Okay, Mr. Gopi, it's not too hot. Okay, so I just put not, then HOT, then I just put S. Okay, so something like that. Okay, just remember, figure out a way to remember this. Okay, so once you have that, okay, the important thing is writing this in a proper unit. Okay, so here I'm going to use, okay, the joule only. Okay, I'm going to use joule only. So 118, okay, you can see 118. Where do we get this? Okay, it's from here. Okay, kilo. So times by 1000. Okay, you have this minus the temperature that I'm looking for, must be in Kelvin. Okay, and then you have this 189. Okay, it's going to be joule. Okay, no need to change. You already changed the enthalpy change already. Okay, then calculate the temperature and you will get 624.34. Okay, you can give your answer like this. Normally, I'll suggest you to give in this form, 624.34, or it's fine to write down as 624 Kelvin. It's still fine, 3 significant figures. Okay, but if in the question they say must use 3 significant figures, then must use 624. Okay, must use 624. Or must use 2 significant figures. Okay, the answer will be 620. Okay, that's going to be 2 significant figure. Okay, so please adjust accordingly. Yeah. Now, solid, okay, lead-2 oxide can be made by heating lead metal in air. So I wrote the equation Pb plus O2 to give you PbO2. So solid, gas, solid. So predict the sign. Okay, so when I see here solid, gas to become solid, it means this is ordered, this is less ordered, then everything become ordered. So it means that it is going to become overall everything is getting ordered. So if it is getting ordered, it means your sign of the entropy change is going to be negative. Okay, what is entropy? Is a measure of randomness, okay, or measure of disorder. So when everything becoming ordered, we don't like, so we just put negative over there. But when they ask you to explain, you don't explain, or they are ordered, less ordered, now become ordered. No, you just explain. How do I, what is the conclusion that I'm getting? Oh, I see this one is going to be oxygen gas. So it's less ordered, but now no gas. Okay, so you can just focus on the gas. Okay, you can say that decrease in number of gas molecules because there's no gas over here. Okay, because of that, okay, your sign, okay, this is going to be what is expected from you. okay, there is no decrease in number of gas molecules. If you happen to give some other answers, I think they will consider. Okay, I think they will consider. But try to use this method. It means that when you don't see gas, okay, just say decrease in number of gas molecules. Okay, if you see all of them are going to be in gaseous form, then you look at the total overall number of molecules and so on. Please decide which one is the best. Okay, okay, that one I leave it here. Okay, so number 5 now. Okay, I think we can finish 5. Okay, completely today. Now, for number 5, okay, describe fully what will be seen, okay, when magnesium and strontium are heated separately in oxygen. Now, this is a AS concept. Okay. Now, Gabriela Nicole was asking, cannot say decrease in randomness. You can say decrease in randomness, Gabriela Nicole, but they don't want to see that. What they want is decrease in randomness. How? Okay. It means they're still asking another question. Why there is a decrease in randomness? Okay, because the number of moles of gas are going to be decreasing. So you need to still answer the basic question over there. Okay, so this one, okay, coming back to question number 5, this is going to be a group 2 metal question. Okay, now you can see here, okay, this is going to be a combination of group 2 and your lattice energy chapter. Okay, because normally group 2 they're definitely going to ask you about lattice energy. Okay, so you can see here, okay, they can ask you a lot of things even in AS. Okay, so you see magnesium, okay, heated separately with oxygen, they will give you magnesium oxide, strontium oxide. Okay, write the equation, but they want to see described fully. So this is not what they want. Okay, they want to hear this one. Now this reaction, okay, both any group 2 metal, okay, when they burn it oxygen, the oxide is going to give us, okay, the white solid, magnesium oxide, okay, barium oxide, strontium oxide, they are all white solid. Okay, so you need to say white solid is formed. You can say that the reaction is a bit slow, and then the reactivity, because as you go down, okay, the reactivity will be more reactive, more vigorous. But I don't think so. When I checked the marking key, they didn't give answers for this. What they were focusing on, the flame. Now, you can see in your AS book, they say bright white flame. If you write white flame, it's also okay. But strontium, okay, they are going to be so vigorous and they will give you a red flame. Okay, that is what they want to see over here also. Okay, it burns, okay, in bright white flame to give you white solid. So for strontium, it burns with red flame to give you a white solid. Okay, so please adjust accordingly. This is from your AS. Okay, write an equation for each of the following process. Include the state symbols. Calcium burn in air, okay, Ca plus O2 to give you calcium oxide. Okay, so balance it, okay, and then write the equation. Okay, calcium oxide is solid. Yeah. Now calcium carbonate is heated strongly. Now this is going to be decomposition reaction. Okay, for carbonate, it will give you calcium oxide plus carbon dioxide. Okay, so you just write down over there. Okay, so it will give you solid. This is gas. Okay. Now, calcium hydroxide, okay, is formed when water is added to calcium oxide. Okay, when water is going to be added to calcium oxide, you are going to get calcium hydroxide. Okay, calcium hydroxide. Okay, okay, this one I hope you remember. Yeah. Okay, before I go further, this is going to be limestone. Okay, calcium carbonate, another name is limestone. Okay, and then calcium oxide, okay, is going to be lime. Okay, so this lime, okay, when you add with water, okay, you are going to get quicklime. Calcium hydroxide is quicklime. Now quicklime, okay, can be in two forms. Okay, if you have calcium hydroxide, okay, in form of solid or powder form, we call it slaked lime. Okay, but quicklime, okay, do remember, quicklime is going to be also known as lime water, okay, when we use to test for carbon dioxide. Okay, so please remember these terms and so on. Okay, describe the main benefit of adding calcium hydroxide or calcium carbonate to the soil. So basically what we are trying to do, we are trying to increase the pH. Okay, so or we are trying to reduce the or neutralize the acid. Okay, neutralize the acid in the soil. You bring up the pH. Okay, you bring up the pH. Okay, so sir, isn't the calcium oxide supposed to be in solid state? It is solid. Maybe it looks like a, okay, so it's solid. Okay, solid. This is gas. Solid. Okay, so solid, and then carbon dioxide is gas. Okay, calcium oxide is always solid. Another way to remember, all group 2 oxides, okay, they are white solid. Okay, you can just remember that. Now, explain why group 2 hydroxide become more soluble in the group. This one, I'm very tired to explain the same thing again. Yeah. So please refer to the notes or the video that I made earlier. Okay, but this one is going to be the SHL. Okay, so why group 2 hydroxide become more soluble? So we are looking at your enthalpy of solution, okay, to become more negative. Okay, so more exothermic. So how can you achieve that? Okay, if it is hydroxide, I told you the lattice energy, the decrease in lattice energy is going to be more than the decrease in your hydration. Okay, because of that, okay, that will make the enthalpy of solution to become more negative. Therefore, it's more soluble. Okay, so please remember, for sulfate, it's going to be the other way around. So for sulfate, it's going to be using the SHL also, sulfate, the decrease in hydration is going to be more than the decrease in lattice energy. So please refer to that. Okay, please refer to that. Okay, so I'll skip this part. Now describe the observation, if any, okay, that you will make when you are adding sodium hydroxide to barium chloride. Okay, when you do that, barium hydroxide, and then you are going to get sodium chloride. Both of them are colorless. Okay, so you don't see anything. Okay, so you can say no change. Okay, no change. There's no observation. When you add few drops of sulfuric acid and barium chloride, this one you must see something, because if let's say there is a chemistry student do not know about this, okay, it's going to be something that is very alarming. Why? If you study chemistry, every student must know, okay, the moment you get barium sulfate, okay, and then you have ACR, whatever, the moment you have barium sulfate, this is a white PPT. You must know this. Okay, you must know this. So definitely you'll get a white precipitate. Okay, see. Okay. Now explain, okay, and describe how thermal stability. Now this thermal stability not only for carbonates, okay, it is also for sulfates. It's also for hydroxides. Okay, it's the same. Yeah. Thermal stability of group 2, when you go down the group, okay, thermal stability increases. Okay, or it means that you need higher temperature, okay, to break the bond. Okay, and we have learned about it in A2, okay, by finding out the relationship with that. Okay, so group 2 generally carbonates, they are very big, more large anions. Okay, and then we have group 2 ions. Okay, group 2 ions, when they go down, the ions getting bigger and bigger. Okay, they're getting bigger and bigger. So we need to talk about the ionic radius, okay, or the cationic radius. Okay, so you can say as you go down, okay, the ionic radius of the cation, okay, they will increase. Okay, when they increase, the charge density is going to be lower. Okay, when it is lower, okay, it do not have enough polarizing ability. Okay, or less polarization as you go down the group. And when you don't have a lot of polarization, there won't be any distortion, okay, of the electron cloud of the carbonate. Okay, when there is no distortion, okay, or when there is no polarization, okay, the bond, okay, between the carbon and oxygen, okay, in carbonates, it remains strong. It is not going to become weak. Okay, so it is going to be harder to break those bonds. Okay, so as you go down, it will become more thermally stable. Okay, whatever that I mentioned over here related to size, related to polarizing power, and then you need to also mention about the, after you talk about polarizing power of the cation, you need to talk about the distortion of the electron cloud of the anion. Okay, then you summarize it. Okay, so that is going to be the one that I want to discuss for today. Okay, the first part of this lesson.